Okay, so it's a pleasure to have with us for the second UK speaker in a row, young Grebik from Warwick, who will tell us about large deviations for graphons. And I put in the chat, sorry, I put to everyone in the chat the link to the slides, so you can download if you wish. And Jan, please.
Okay, so thank you very much. So yeah, well, thank you very much for the invitation. So I want to talk today about large deviation principles for graphons, and I have to say that it's a joint work with Oleg Pikhurko, and it's still in progress. So we are writing it down, and also what I want to mention is that similar papers appeared on Archive, or papers mentioning large deviation principle for graphons, and it's not really clear to us what is the exact connection to what we do. So maybe if you know something about these other papers, then maybe then we can talk about it. So I mean, the main one is work of Borgs, Chayes, Gaudio, Petty, and Sen, who has a paper about large deviation for block models. So maybe I can then comment how I understand is the connection between our work and their work, but maybe you know something about their work also. Okay, so what I want to talk about is large deviation principle in the case when you sample from a general graphon. So what Chatterjee and Varadhan did, they sampled from a constant graphon, and this was basically the beginning of, as I understand it, large deviation principle for graphons. So let me start with some motivation and what they did, and then you will see what is the generalization that we consider. Okay, so let's start. So we fix a real number, and then we consider the Erdős Rényi random graph. So you have n vertices, and you put an edge with probability p between I and j independently for every I and j. So this describes the random graph that is called the Erdős Rényi graph with parameter p, so g and p. And so now, because you make independent decision for each edge, it's easy to see what are the expected numbers of edges or triangles, or basically any graph inside your random graph. And also it can be proved that these numbers concentrate. So what do I mean by that is that if you sample from this G and P, then with a very high probability you will see the number of triangles close to the expected value. Okay. So this is the basic setting. And now what Chatterjee and Varadhan considered, or what is the question that was interesting, is what can you say if what can you say about a rare event of having more triangles than you expect? But you can ask about any other rare event, like having anything. But let's stick to the triangles, because as you will see, only even in this case, things will be interesting. And the question is what is the probability of this rare event when you send n to infinity? What is the asymptotical behavior? And is there a typical behavior? So when you suppose that this rare event occurs, is there some typical element inside this rare event? Okay, so now the answer, that would be ideal in the sense that it would be easy answer, not that there is some evidence for it, I don't know, would be that like the rate is given like this. So that means that basically the decay is given by the n square, and this IPR is the entropy function that I will define later. But like, I mean, this is just some kind of illustration, so don't worry about this formula. And what would be very nice if the typical graph when the rare event occurs is the Erdős graph with the parameter r. So that would basically say that to have more triangles means that you need to have more edges, and they are like uniformly distributed among the random graph, inside the random graph. Yes. So that would be like the ideal answer, but it is not. It is not like this. It is not like this. So what Chatterjee and Varadhan showed, that was the surprising result, that there is some kind of like a phase transition even in this like easiest case, right? So we fix P, and then what they prove is that something like this can happen if P is like small. So if R, so there are two numbers, delta 1 and delta 2, and if R is between P and P plus delta 1, or between 1 and between P plus delta 2 and 1, then the typical behavior, so I'm always talking about this triangle count, behaves like the typical graph in the rare event behaves like this Erdős graph with parameter R. While if you are in between delta 1 and delta 2, then it's not true. Something else happens. Yeah, so I don't think it's clear what exactly happens, but something else happens. Okay, and now people now know what is like the exact relation between these two numbers. So this is P here and R is in here. And now when we have P, when you fix P and you just consider this R like bigger than P, then if you are inside this, then the symmetry breaking occurs. So it does not behave like the Erdős graph with parameter R, while when you are in here, it behaves like this Erdős graph with parameter R. And there is some like, hopefully I wrote it correctly, the formula for the for this curve here, hopefully. Okay. And how people prove things like this? So that was introduced by Chatterjee and Varadhan, and that's like when the large deviation occurs. So they proved LDP, a large deviation principle. So the question is, where did they prove it? Like, because the G and P distribution is on like graphs on n vertices. So this is for each n basically a different space. But they prove it in like one particular space where you can embed all these graphs, and this will be the space of graphons. And once they had this, the other task is to understand like these solutions for the variational problem. So I will not speak about variational problem. I will only speak about LDP. Also, I don't think that I could even speak about this variational problem because, yeah. So I think that like my knowledge is kind of limited in that part. Yeah. So it will be only about LDP. And now I want to, so basically this was the motivation. Like you have the random graph, you expect some number of copies of triangles or any other graphs inside your random graph, and then you just ask about the rare event that there will be more than expected number. And what they prove is that like there is some large deviation principle, and you can use this large deviation principle to describe what what is like the asymptotical behavior of the rare event, and whether there is a typical behavior. Yeah, so this is like the motivation, like the motivation for them, and I think it's still a motivation. Yeah. Okay, so now, as I said, they proved the LDP, and they proved it in the space of all graphons. So what are graphons? So graphons are limit objects for converging sequences of dense graphs. So dense graphs means that the number of edges in this sequence is asymptotically n squared. So it's not linear, it's n squared. So there's a lot of edges. And actually there is a space of all limit objects or these sequences. And yes, they are called graphons, okay. So what is the convergence? It's the homomorphism density convergence, or equivalently it's this cut distance convergence. So I will comment, I will say something more about this. Like what are these two on the next slide. But what are the limit objects? So they have like a nice description, and they are like measurable symmetric functions modulo some weak equivalence. Yeah, so like it can happen that two functions are considered to be the same element of the graphon space. So I will also comment on the next slide. How can this happen? And the graphon space, we denote it by this curly W with tilde, together with this cut distance, is a compact metric space. So that's the main result about the graphons. So yes, so basically there is a space of limit objects, and whenever you have a sequence that contains a lot of edges, like every graph in the sequence, then it converges to some non-trivial measurable function. Okay. So what is this convergence? So like a graphons Vn converge to V. If when you test against each like finite graph F, the homomorphism density converge. So what is this homomorphism density? Well, this is just basically you integrate. So when you just fixed a k-tuple of elements in the interval 0, 1, this expression here just tells you what is the probability that this k-tuple, like what is the probability that this k-tuple corresponds to a homomorphism from this graph F. So basically, when you give me ij and it is an edge, you consider the value of this function. So recall that u is a function from 0, 1 square to 0, 1 that is symmetric. Okay, and this is the same. This is like the infinite version of like a classical homomorphism density. So when you give me a finite graph G, then you consider the set of all homomorphisms from F to G, and you divide by the number of all possible maps. And like this thing should be like infinite analog. When this U, like the graphons as a functions, are considered as like infinitesimal analogs of adjacent symmetrics or something like that. Okay, but I will not like so basically what you need to remember is that this is like it's a compact metric space, and that the topology is basically given by homomorphism densities. That's the only thing that you should remember, not this formula. Okay, and so now what Chatterjee and Varadhan did? Well, they take this random Erdős Rényi random graph with parameter p, and they represent it as a sequence of Borel probability measures on the graphon space. And then they showed that on this space, this sequence satisfies large deviation principle with speed n squared. And like, how do they represent this Erdős Rényi random graph inside the graphon space? Well, there is a very canonical way how you can represent a finite graph as a graphon. So as I said, like there's this adjacency matrix for G, so you can just represent it. You can just use this to like represent it as a function. So now I will make a picture that would hopefully make this clear. So by the way, if there are any questions, just ask. Yeah, so I see. So now do you now see the whiteboard? Yes. So basically, when we have a finite graph G, it can be, I don't know, on 4 vertices, like this. So the canonical way how to represent it as a graphon is just that, like this is the interval 0, 1 times 0, 1, and then you just split it into like 4 measurable sets that have measure 1 over 4. And now, for example, this is like the set A2 that corresponds to this number, to the vertex with number 2. This is A4. And because there is an edge here, you just put like the value here will be 1. Okay. And between 1 and 4, there is no edge, so there will be like value 0. So here is value 1, and here is value 0. So this is basically how you can represent the finite graph as a graphon. And like similarly, if you have a weighted graph, so what is a weighted graph? Well, here you basically have all the edges, but for example, for this edge, there is some value between 0 and 1, which is the weight. Well, then what you can do is that you can again represent this as a graphon. So this is G. So you can represent this again. So this is the set A2 and this is A4. So then the value here will be exactly this value. So this is kind of like a canonical way how you can represent finite graphs or finite weighted graphs as graphons. And also, let me just say that like the compactness of graphon space basically follows from Semerardi regularity lemma. And similarly, what follows is that the functions that are called step graphons are dense in the space. So what is a step graphon? So step graphon basically means that you partition your domain into finitely many sets, and then this function, I don't know, u, which is this step graphon now with 5 steps, needs to be constant on each of this rectangle here. But these sets like this set need not necessarily be an interval. It can be any measurable set. Yeah, so basically for each step graphon, you have this partition into sets, I don't know, like k many sets, if it's a k step graphon. And functions like this are, things like this are dense in the graphon space. Okay. So, like, so basically, now that you know how to represent graphs as graphons, you can easily represent this distribution inside the graphon space via like this push forward construction. So basically, what you do is you give me an event A, which is a Borel subset of this space. And then this P and P, like this probability of A, is basically the probability that this representation of the random graph will end in this event A. So yes, hopefully this is written, like it makes sense, this formula. So again, it's a probability that when you assign to a random graph that you sample according to this distribution, its graphon representation, you will end up in the set A. So now, of course, this measure for each n is atomic and it's supported only on finitely many points because there are only finitely many graphs on n vertices, right? And now, well, in the beginning, I said something about concentration. So now, now in this graphon space, you can kind of like formulate it in much compact way. Let's say using this cut distance. So I said that the expected, when you sample from this Erdős graph, then the expected number of, for example, triangles will be very close to the expected, like the number of triangles in a sample will be very close to the expected number. And you can say this compactly using this cut distance, that whenever you fix epsilon, then the probability goes to 1 of the like epsilon neighborhood of the constant graphon. So before P was just a number, but now you can represent this number as a constant function in the graphon space. And this concentration just means that for each epsilon, the epsilon neighborhood of this constant graphon in the graphon space, the measure will tend to 1. Okay, or in other words, this means that if you like sample according to one of these measures, no, if you just pick a random, no. Okay, let's just leave it like this. Okay. Okay, so now because you have this concentration, I think it makes sense to talk about large deviations. So again, let me make some picture. So basically how I view these large deviation principles is that you have this like big space, I don't know, X, with a sequence of measures. And there is some like significant point here. And now whenever you give me an like epsilon neighborhood of this point, so for every epsilon, these measures, the measure of this epsilon neighborhood tends to 1. Okay, but now if you just give me any other point here, some y, then you can just ask what is the asymptotic behavior of the decay around this point, basically. So yes, so I mean, this is equivalent to like the standard definition of LDP when you are in a compact space, which we are. So what I mean by it, that you somehow imagine like infinitesimal neighborhood around here, some by, and now you basically ask what is the rate of this event. And if you have some speed epsilon n that goes to 0, then if there is a chance to have LDP, then it should be something like this. Okay, when y is the rate of decay. So this is how I like view it. So like you have a compact metric space or something, or a compact space, and there is some significant point such that everything concentrates around this point, and then you just try to investigate what is the decay around around other points given some speed epsilon n. Okay, so this is like the mental picture that I have in my head. But so now, okay, now we can like make it formal. What does it formally mean? Large deviation principle. So you start with some topological space. And so function I is called the rate function. If the preimage, so it goes from x to interval 0, infinity, and infinity is there. So it can attain value infinity, but for each non-infinity value a, the preimage of the interval 0 to a must be closed. So in our case, everything will be compact. So good rate function is the same as a rate function. Okay. And now, as I said, you have a sequence of measures and some speed. And then you say that this sequence satisfies this large deviation principle on x with this speed and a rate I, if something like this is satisfied. So whenever you give me a Borel set, then the lim-inf, like asymptotic behavior of this expression, is bounded from below by the infimum of these rates of elements that are in the interior of F, while the lim sup is bounded from above by the infimum of these elements when you take the closure of F. And so, as I mentioned, in the compact space, this is kind of the same as like considering the infinitesimal neighborhood of any given point, and then the rate around this point should be exactly the I of this point. Yeah, but I mean, this is the formal definition, so this is like the real definition. Okay. And now finally, I can state what they proved, Chatterjee and Varadhan. So recall this is the entropy function. So like given A, you compute like what can you say about B given A? And then Chatterjee and Varadhan proved that this sequence, when you have this parameter P, satisfies this large deviation on the Graphon space with this speed. And this good rate function. So basically what you do is that you consider any x and y, and then you compute the entropy of this value with respect to P, and then you integrate. So what you need to show is that, I don't know, like this is a good rate function that it does not depend on the representation of a graphon, because I said that in this graphon space, two functions can represent the same graphon. So for each representation, this should be the same. But this all can be proved, and I mean this is the main theorem that they had, and this was like the start of the large deviations for graphons. Okay, so like to summarize what I just said from the beginning is that there is this Erdős-Rényi random graph. You can represent it as a sequence of Borel probability measures on the graphon space. This sequence concentrates around the constant graphon P, and it satisfies this large deviation principle with this speed and this good rate. And what I will not talk about, you can use this to solve the variational problems and describe typical elements in some interesting rare events. Okay, so this is what they did. And now what we want to do is that we want to basically replace this small p by sampling from any graphon, but fixed, but not necessarily a constant graphon. Okay, so yeah, so now I will, like the rest, I will talk about what do we know when you sample from a general graphon. Yeah, so are there any questions about this, or is this hopefully at least a bit clear?
So, okay, I think, but if anyone has any questions, please do ask.
Okay. Okay, so now I want to define what is this sampling. So basically there are two canonical measures or distributions that you can sample from a graphon. But mostly I will speak about this that corresponds to this P that was there. So we fix a graphon, and now we want to define a distribution on n vertex finite graphs. Or using the same construction, this is basically the same as describing like the push forward, which we denote like this. So this P and W will again also will be only concentrated on the graphons that are representations of finite graphs on n vertices. So before I define this sampling, so this same construction, I mean the same for this push forward. Yes, so like again, the probability of the event A is just the same as the probability that the W random graph will end up, the graphon representation will end up in A. So this is just, I just repeated twice how to get this P and W from this distribution. Okay. But again, before I state it, there is the same concentration, which is like the yes, like the same concentration as in the constant case. So what does it mean? So you give me this W, it's element of the graphon space, and you consider its cut distance epsilon neighborhood in the graphon space. And again, if n is sent to infinity, this will concentrate. Like the sampling, like the measures obtained from W will concentrate around W. So this is just the definition that this is the epsilon neighborhood in the graphon space. And this can be, you can say this in other words using this finite distributions on finite graphs, that if you sample a finite graph, like with a high probability, the sample will be close to W. Again, in this cut distance, in the homomorphism density distance. Okay, so now what do I mean by this sampling? So again, let's switch here. So I said that there are two sequences. So let's first like speak about this one. So what does it? How do you get this? So basically, you want to sample a graph when n is fixed on n vertices. So what you do is that you have now here the interval 0, 1. And for example, you have 4 vertices. So you just randomly map them here. So you obtain 4 points, some x1, x2, x3, and x4. Now you go in this graph on W, and these 4 points, they now have some values. So for example, this is the 4th point here, and this is the 1st point here. So there is some value. And now, like independently for each I and j, you put an edge with this probability. So what you obtain in the end is some graph on 4 vertices, and there are some edges, and I don't know, it can be like this. Yeah, so basically there are two steps in this sampling. First, you randomly pick like 4 points in the interval 0, 1, and then independently, according to the value, to this value, or here, you just decide whether there will be an edge or not. Okay, so this describes. I mean, this describes actually this GN W. So this is a distribution on finite on graphs on n vertices, but you can use this push forward to define this P tilde n W. Okay. So this is one way. This is one way how we can sample, but there is another like canonical measure, and for some reason it's much simpler to work with this. And this is this H n W. So what is H n W? Well, basically there will be only one step, only one, like there are two steps in here. Yeah, so first we sample the points and then we round the edges. So we will not round the edges now. We will not round the edges. So again, for example, we have 4 points. So we just sample them. But now you will only remember the values. So you will remember this value. So it was again, I don't know, x1 and x4. So we will not round anything, but what you will now obtain is this weighted graph, where, for example, here the value, the weight will be W of x, y, and x4. And like similarly for each edge, you will have some weight given by this. So this again gives you a Borel probability measure on the graphon space, because now you can again represent every weighted graph as a graphon. Okay, so again the difference is that in this P and W you round the edges, but in this H and W you don't round the edges, you remember the numbers. You get weighted versions. Okay. So now if we go back to the slides. So this is exactly what I said. Here you get 2 steps of randomness, so you pick a random n tuple, then you round the edges according to these values. While here you only pick the random n tuple. And then you remember the values. Okay? So now what we want to do, we have fixed the graphon. We have 2 sequences of Borel probability measures on the compact graphon space, like 2 versions of W random graph. And now what we want to understand is this large deviation principle for these 2 measures, these 2 sequences. Or I mean, this one is probably the more important one, but it's nice to work with this one. It's like nicer to work with this one. So some observation to be clear that like we understand what I try to define is that if you have a constant graphon, then this H is like a Dirac measure on the constant graphon, because if you just pick a random n tuple, the values will be this constant value all the time. So then when you represent it back as a graphon, you obtain a constant graphon. While if you have 0, 1 graphon, that means that it attains values 0 or 1, then there is no second step of randomness. So like you don't round edges because everything is determined. So these are the same. And you can prove that actually both sequences concentrate around W in the sense that for each epsilon, the epsilon ball around W, the measure tends to 1. Okay? And so why do we talk about this? Because there is some notion of exponential equivalence. And this sequence is like easier to work with. So what is this exponential equivalence? So if you give me a speed epsilon n, then the 2 sequences of measures on some let's say compact space X are exponentially equivalent if one satisfies LDP with this speed and rate I, if and only if the other one. And now the first thing that we observed is that, so this is just how you should compare speeds. So basically, if the speed is slower than 1 over n square, then these two sequences are exponentially equivalent. So as I said, it's easier to work with this. So once you, for speed that is slower than 1 over n square, once you can determine what happened with this sequence, it automatically will hold for this sequence. Yes. So what I just said is that there is some connection for slow speeds of these two sequences. And now I will finally summarize what we understand and what we don't understand about this sequence. So I will now talk only about this sequence, and I will just basically in the proof use that they are exponentially equivalent. Yeah, so I call it a theorem, even though there will be some question marks. So it's not really surprising, but somehow I don't think that the proof is easy. It uses some classical theorems from functional analysis. So if your speed is actually slower than 1 over n, then there is large deviation principle, but the rate is trivial in the sense that it's 0 on the graphon and it's plus infinity elsewhere. Okay. Then for the speed, things for 1 over n, so things are starts to be non-trivial. And you got some non-trivial large deviation principle, and there is a good rate function JW. So I will try to talk more about this, define this rate function. Then when you are in between, again you have LDP, but it's again 0 or plus infinity, and it's 0 on some set R and W that we call Radon-Nikodym copies of W. So I also try to define, if I have time, define what is this Radon-Nikodym set for W. And now the most interesting speed, so there should be 2 over n square, but yes, it's not clear what happens in general, yes. But when you have a step graphon, then we can prove that there is a large deviation principle, and again with some rate that I will hopefully define. And if the speed is faster than 1 over n square, then again you have large deviation, but it's 0 on some set of forbidden patterns or something like that of W, and it's plus infinity elsewhere. So now basically, when you give me a graphon, you can pretty much, except for this case, this is the most important case, understand what is going on. And if you give me a step graphon, you can fully understand what is going on. So let me just say that if W is a constant graphon, then these first 3 cases are the same. And this Radon-Nikodym of W is just W. So in Chatterjee and Varadhan, this would be, in their case, nothing is happening here. While if you give me this 0, 1 graphon, this W is 0, 1 graphon, only attains value 0 and 1, then 4 and 5, nothing is happening. Everything already happened in 1, 2, and 3. Okay. So I have a visual picture of this. So you have the graphon space, and here is the main guy, the graphon that you sample from. So if your speed is slower than 1 over n, it's the LDP is 0 here and plus infinity here. While if your speed is this 1 over n, there is this Radon-Nikodym copies of W, where something non-trivial is happening while it's plus infinity outside. If your speed is in between 1 over n square and 1 over n, it's 0 on this set and plus infinity outside. Then if you are not a step graphon, it's not clear what is happening here, but there is some set of like forbidden patterns, and outside is plus infinity. So if there is a large deviation principle, the rate must be 0 on this Radon-Nikodym set and plus infinity outside. And if you are faster than 1/n², then it's 0 inside this set and plus infinity outside. Okay. So yeah, so I have like 15 minutes, so I'm not sure. So I should what I wanted to do is now comment like on all these cases. So I don't know if I will make it to speak about all of them, but let's just start with this Radon-Nikodym.
So pick the most interesting ones.
Yeah. Okay, so let's start with this 3 because, or let's say with these two. Okay, so what are these Radon-Nikodym copies? Because somehow this will be also like important to know what is this in the 1/n² case, which is probably the most interesting one. So I need to anyway like define what are these copies. So suppose that W is a step.
Maybe first there's a question in the chat. So Jonathan was asking if you can give some typical examples of speed 1/n or the speed much smaller than 1/n², the very small speed. It would be good to look to see some examples of that.
So like okay, so this speed, like this fifth case here, I can say what is this forbidden thing, and I hope that this will answer the question. I don't know. Okay. So yes, here. So basically, this forbidden set. So you have this W, and for some finite graphs, there are no induced copies of G in W. So for example, if W is bipartite, then there is no induced copy of a triangle because, you know, it's not possible because at least 2 elements would be in one partition and there is no edge. So if like it's a bipartite graphon, then it has no copies of triangles. And this set forbidden consists of elements that would also have no copies of triangles. So yeah, so I mean, like this is what happens in this speed if it's really fast. So I mean, for example, if W doesn't attain 0 or 1, then this is always everything. So it's like only in very special cases, like for example when it's bipartite, that you can distinguish something or you can see something non-trivial. Yeah. I hope that this at least gives some hint of what is going on. Yes, but I would rather speak about this 1/n because I mean here we'll see like what do I mean by these Radon-Nikodym copies and what is this rate function for 1/n. Okay, so I hope that's at least I hope that I answered the question at least a bit, or hope Jonathan is satisfied. I don't know. Okay. So what are these Radon-Nikodym copies? So suppose that you have a k-step graphon, so you have a partition into k sets. They need not have the same measure, just any partition. And it's a step graphon. That means that on each ai times aj, it attains a constant value qij, which is in the interval 0, 1. Okay. So now, like if you give me any other k partition, even such partition that some of this bi can have measure 0, then you can define a graphon that corresponds to this partition that is obtained from this W. So namely, it will also be constant with value qij on this bi times bj. But now the sets could have different measure than the original sets ai or aj. So for example, B1 can have measure 1 and all the other sets could have measure 0. So this will be a constant graphon. Or BK can have measure 1. Anything like that is possible, is consistent basically, let's say. And now these Radon-Nikodym copies is the collection of all such graphons get from W using any K partition. So basically what you are allowed to do is to stretch or shrink these sets, but they need to remain a partition. And now this rate function measures how difficult it is to transform W to this representation. So somehow in this step graphon case, this is very close to like the Sanov theorem, like the LDP for empirical measures, because basically what you do, I mean, after you can switch from this like measures P and W to this H and W, you basically just define, when you sample this H and W, you basically need to decide how many points will go to what sets this A1 up to AK. So you have n points and you just need to decide what points will go to A1, what points will go to A2, which is basically the same as like in Sanov theorem, where when you have like this finite alphabet, you have some distribution and then you sample like long words and then you just consider the empirical distribution given by the sampling, right? So this is actually very, very similar in the case of step graphons. So I wanted to make some pictures, but I don't think that I have time to make this picture. So hopefully this was clear. So basically what you do is that you just start with one partition, then consider all other possible partitions. But in general, when W is not a step graphon, so suppose that this is like your W, you can basically just shrink the domain, or like stretch it or do something like this. And then, like formally, what does this mean? This just means that you consider all the possible like Radon-Nikodym derivatives. So you have like elements of L1 that have norm 1 and are positive. And these basically describe how you can stretch the interval 0, 1, right? So basically this F transforms this Lebesgue measure into some other measure. So maybe this new measure will be more concentrated in the middle. Maybe it will be more concentrated on the right, but it will definitely be absolutely continuous. It will not be a Dirac or anything. And now when you give me such a F, then you can define this graphon W with index F to be the function that formally takes the same values. It's defined on the same space 0, 1 times 0, 1, but there is this new measure on the vertices. It's not the Lebesgue measure, it's this other measure that you get from F, the Radon-Nikodym, such that the Radon-Nikodym derivative is F. So like formally this is not a graphon in the graphon space as we defined it, but like this space could be like there is some measure preserving transformation that sends like that transforms this space with this measure into the interval 0, 1 with Lebesgue measure. So you can like push forward this graphon and obtain like a proper element of the graphon space. Well, and now basically as in the like Sanov theorem, what happens is that like the rate of U will be the infimum over all possible like expressions of this form, like the price that you must pay to transform W into U, but in the cut distance. So there could be many ways how you can take F. and how you can, like many Fs that could transform W into U. So you just take the infimum, like the less, the minimal price that you have to pay. And this will be the rate. This will be the rate. And now this Radon-Nikodym set is just like you take the set of all guys that have rate between 0 and plus infinity strictly, and then you take the closure. So basically this says that there is some kind of stretching that happens for the speed 1 over n. Yeah, so like in this general picture, like if you just focus on 2. So as I said in the proof, you work with this H and W. Okay, so again, 1 and 3, basically you use some standard, but let's maybe a deep result. But in 2, which is like the most interesting in here, you use this Eiselbacher-Schmock like version of Sanoff's theorem, but also like some kind of very big generalization of it that uses like weak topology that are even not metrizable or something. So somehow there are some deep theorems that you can use on the way to like then get that this JW is like a good rate function for the speed 1 over n. But basically there is like a new phenomena of this stretching and of this like Radon-Nikodym versions that you cannot see for the constant graphon, because no matter how you stretch the constant graphon, it will still be a constant graphon. Like it doesn't change. Yeah. So yes. So let me just briefly say that if you just only work with H and W, then here in this bullet point 3, you can just erase this 1 over n square, and this describes the whole behavior of this sequence, all the LDPs that you can have. So like for this sequence, everything is known, which basically implies that when you have 0, 1 graphon, then you know everything, because these are the same. Okay, so then there was this number 5, but I already said something about it. So let me just like finish, because I don't know, I have like 3 minutes or something, very quickly about this mysterious speed 1 over n square. So basically, because with the speed 1 over n, you can zoom everywhere. You can like stretch or forget about some parts. Even like small patterns will appear in the speed 1 over n square. So what do I mean by it? Is that if you give me a sequence of graphons that is dense in the graphon space, and then you just glue them together on the diagonal to create a new graphon W. So now when you sample from this W, then the space of Radon-Nikodym copies is everything, because even though like the size of this or the measure of this set is 1 over 4 or something, because you can zoom everywhere, you can make it, you can like stretch it and make it like a proper, like this will have something like log 4 or something like that, like the rate for the speed 1 over n. So for the speed 1 over n square, it must have rate 0. So in this case, you will not see anything for the speed 1 over n square. Like this is like example that says that if you just take some crazy graphon that sees basically all other graphons, it's possible that you will not see any behavior for the speed 1 over n square. And now like for these step graphons, you can prove something because there are not that many patterns when you zoom. Like basically when you have this step graphon, you only see either like the skew P, or you just basically move the size of this set or of this set. And then, yes, so, I mean, I don't have any more time, so let me just say that for step graphons, that you can define the rate, and it's very similar to the Chatterjee and Varadhan, but you can basically place these steps anywhere. You have something like more freedom what to do. And let me just finish with some problems. Okay, so what we don't know, or we will think about it, let's say, are like the possible applications for the speed 1/n. So maybe you can get some solve some variational problem there, or maybe it is easy, but we haven't thought about it, I think. So that could be one thing that we don't know. And then what I said, what happens for general W, but that seems to be, yeah, we spent some time and we don't know what's happening for this speed. So let me just say that since we know what happened for step graphons, most likely we know what happens for continuous graphons because you can approximate them nicely with step graphons. And also because, like, the same reasoning, if you understand graphons of this sort, like 1/3 plus 1/3 times the characteristic function of some ugly set A that is like symmetric subset of 0, 1 times 0, 1, then maybe this is enough to understand the general case. But somehow it's not clear. Okay. Yes, so this is everything.
Okay, thank you. So I will unmute everyone to thank Jan.
Thank you.
And I will stop the recording, but we can have some more questions if people wish.